So let's continue on the notion of scheduling or real-time scheduling. What we discussed last time were a few definitions that affected the way the way we intend real-time system tasks. As you remember, task was an execution flow that often is periodic, that provides some worst-case execution time in the simplest model, a period, or a minimum interval time at which two jobs of the same task repeat themselves, are periodically or sporadically released, and the notion of deadline, so the moment by which the task should have finished the execution. The deadline may be equal to the period, may be shorter, larger, whatever. Before analyzing scheduling algorithms for periodic or sporadic tasks of recurring activities, we have today a set of slides following for those tasks which are not periodic. So just random tasks that arrive in your system without any periodicity, okay? These are just batches of execution that may arrive whenever, okay? Whenever you want. They have often an associated deadline, so you know real-time tasks should have a deadline. But again, we were not referring to recurring activities, just in this set of slides to jobs that may aperiodically arrive, okay? We will later deal with periodic arrivals, and then we will accommodate aperiodic arrival again through the notion of real-time servers. So now it doesn't mean anything to you, but it will mean in a few classes. Okay, so set of definition, then some non-real-time scheduling algorithms that we can use that have some nice properties. We will see, for instance, the shortest job first scheduling algorithm, and then we will move back to real-time scheduling algorithms. So, definitions. What is a scheduling? Scheduling is the process of selecting an execution flow, a task, a thread to be executed next. Okay, it's a very simple operation, can be that complex, but by which we select among the tasks that are ready to execute which one we will assign the processor to. Okay. In general, we have different kinds of scheduling, and we schedule different kinds of resources as well. So between the temporal notion of scheduling, we have long-term, medium-term, and short-term. So long-term scheduling, these are very high-level concept, means before I create a process, a given process, decide if it must be activated or not. So decide when to activate a given process. Medium-term scheduling means this process, shall I swap his context from secondary memory to main memory, or it is a process that I rather don't need now, so I will leave his context in the secondary memory. And short-scale scheduling, which is what we are most concerned with, is essentially the activity of deciding which process to execute next, okay, right away, which is the next one we need to execute, okay. Short-term scheduling is the one that we... Yes?
Can you repeat the definition of long-term scheduling?
Yeah, so basically if I have a process, whether I need to activate it or not. So is there any activity that I need to activate in the future? Okay, not now, not right now, but is there anything that I will... Exactly, yes. Okay. But again, we are not much interested in the medium and long. We are mostly interested in the shorter scheduling problem. So these are the slides that you already saw in the previous cycles. So we have different states of my task that may move from ready or suspend to new, from new to ready suspend, from new to ready. Medium-term scheduling basically decides whether a ready task should be temporarily set back to secondary memory. Okay, this is for instance a task that I won't need for a while. Okay, and short-term scheduling, this is essentially what we are more interested at. So from ready to running, okay, which one among the ready tasks are to be executed on the executing course. Okay. Again, so medium-term scheduling can be either a ready task suspended or a block task to suspend it. So I have a task that is blocked waiting for some resource or for some I/O. I will put this context back to secondary storage. Okay, I don't need it right now. Of course, the process of bringing it back to main memory will be expensive. Okay, so it's a trade-off, of course. If you need to free some main memory for other tasks that are likely to be executed in the medium term, then it's okay to do that. But then when you will need to reload it from secondary storage, then it will take a while. Okay, so this is kind of medium-term scheduling activities. Again, we are not much interested into that problem. So, in the long-term scheduling has to do with some admission tests. We will deal in this course with some algorithms which are not scheduling algorithms, but they are schedulability algorithms. These are two very different notions. Scheduling algorithm, again, is the algorithm according to which I select the next task to execute on the core. Schedulability algorithm is instead a test that I make which tells me, given a set of tasks, either periodic, aperiodic, whatever, whether they satisfy the timing guarantees specified by the application providers. I repeat, schedulability test is an algorithm, a test, that tells me whether one or more tasks will be schedulable, will be possibly executed according to some scheduling algorithm on one or more cores, so that all deadlines are met. Okay, we will get back to this concept, to this notion later. This is just to tell you that in real-time systems, before deploying our tasks on the actual platforms, it is best if we know by design that all deadlines will be met. We don't just put them, schedule them, and see whether deadlines are missed. We do some analysis beforehand to understand whether the load, the utilization of the processor is sufficiently low to get all tasks respecting meeting their deadlines. Okay, let me repeat again. So, scheduling algorithm is something that at runtime takes one task, gets into the processor, and executes. Schedulability algorithm is something that, okay, tell me what task do you have now in your system. I will tell you whether all deadlines will be met. Okay, according to some scheduling algorithm. Okay, so for instance, if I have two tasks that execute, that's a very, very simple test I can make. So I have task 1 and task 2. And task 1 executes for 2 time units every 3 time units. And task 2 executes for 2 time units every 3 time units. Okay? And I have just one core. Okay? So that means task 1 arrives, executes for 2, then re-arrives, executes for 2, or re-arrives, executes for 2, and so on. And the same for task 2. Okay? With your intuition, would that task system be feasible so that all tasks complete their execution before the next activation? Let me repeat. I have 2 of these tasks, okay, execute for 2 every 3, 2 every 3, 2 every 3, 2 every 3, and so on. Would this task system, task set, be schedulable on your single core architecture? Of course not. because every period you have 2 out of 3. So if you compute the utilization, we will see that more in detail later. But if you compute the utilization, utilization is the ratio between execution time and period. Okay? So you have 2/3 plus 2/3, and that means 4/3. But the execution time that I have in my system cannot exceed 1. Okay? This is a single core process. Okay? I cannot execute more than 1 task at a time. If I have 2 of these tasks that every 3 time units need to execute 2 plus 2, I need 4 time units every 3 time units. Okay? So this task is not schedulable. Okay? So this is a schedulability test. Okay? I can do admission control. I can do admission control, which has to do with long-term scheduling. Okay? Now to clarify better your question. So if I have my system that now is executing a task with 1 out of 3, 2 out of 10, okay? I have tau 1, tau 2, and now a new task arrives, task tau 3, which would like to execute 1 out of 2, okay? It asks, can I enter the system? I have a schedulability test that computes, according to some given scheduling algorithm, whether this task can enter the system without causing any deadline miss. Okay? That's a feasibility or a schedulability test. Okay? If the answer is no, you can either reject this task from the system or make space for the task by rejecting some other task in the system. Okay? This is long-term scheduling. Okay? Whether to allow a new task to enter the system or not. Okay? You are not deciding which one of the 3 or 2 is executed in the next time unit. You are just deciding which one allowing to enter the system. Okay? Once you allow them to enter the system, okay, now for instance I rejected this guy, now I have the short-term scheduling problem. So which one to execute next? For instance, I would like to execute tau 1. Okay? And then I execute tau 2. Okay? And then no one because no one is ready. And then, yeah, tau 1 arrives again, okay? And then no one is ready, okay? Then tau 1 again. So this is like a short-term scheduling problem. The long term is whether to admit one of these tasks in the system or not, okay? Did I clarify better the notion? Okay. Yeah, so if the way we decide in the long term which task to allow to enter the system, of course, has an impact in your system. So typically in the automotive domain or industrial automation, you don't have tasks dynamically arriving in your system. So typically in a car, you don't allow anyone to execute their code like you have in your desktop. Okay? So the software in a car is predetermined. Okay? You may allow in the recent architecture the user to download some infotainment application and stuff like that, but these applications typically are containerized into some real-time server that allows them not to interfere with the rest of the system. Okay? You cannot allow in a car that some software of anyone will interfere with the engine control or with, I don't know, the chassis control or with an autonomous driving system, you know. So this is the way automotive tasks or industrial automation tasks are done. So you typically have a very initial admission control, and then you don't allow any more tasks to enter the system. Okay? While in a soft real-time application, like if you have a game or a VR headset, virtual reality headset, you may allow some new task to enter the system or not. Okay? Or you have some database, you have some cloud computing real-time application. So these are soft real-time applications according to which you may allow some new activity to enter the system if the quality of service that you will be able to provide will be sufficient according to your parameters. Okay? So you may do a schedulability test. I have free space for a new job, a new task to enter the system, okay, allow him to enter. I don't have any space without sacrificing QoS or deadline miss of the existing task, then I reject it, okay? This is dynamic admission control. Okay? It's typical for soft real-time application. For hard real-time application, we typically do not have it unless we containerized these soft real-time activities in real-time servers that we will see towards the end of the theoretical part. Okay? Okay, the medium term is the part of the operating system that has to do with swapping in and swapping out a given context of a process. Process is in, it was admitted to the system. I just need to understand whether to keep it close to the memory level, close to the processor, or storing it back to the secondary storage medium. Okay, so again, we are not much interested into that. Okay, of course, if it is a thread that is going to be often executed, it's better to keep it close to the cores. Okay, its context is better kept in the central memory. Okay, if it is just a batch activity that has to execute once every I don't know 30 seconds, then you can conveniently take it on and back to your secondary and primary storage. Okay, so let's move to what we are interested to. So short-term scheduling. We have two stages. It's not in the slide. So one is taking the scheduling decision, and the other one is dispatching the scheduled task onto the core. Okay, so the schedule function, the selection function, is complying with the scheduling algorithm. So if you remember, I told you that we typically have one or more ready queue, so this data structure which hold the tasks that are now ready to be executed. So with some kind of algorithm, I need to decide which task to take and put to execution, which task to dispatch to the core. Okay, if I have multiple cores, then I will need to decide, of course, multiple tasks, take them and schedule them on the available cores. Okay, so the selection function is the function that decides which process to select from the tasks that are ready, okay, according to some scheduling algorithm. Okay, we are going to see multiple scheduling functions, multiple selection functions. Okay, right away today we will show from the simplest one, first in, first out, okay, to more complex ones. Okay, so when the decision is taken, so when I selected which task to execute next, okay, so either there is a task running or not, so I take the decision on which task to execute next, okay. When I took that decision, the decision mode may be preemptive or non-preemptive, okay. So preemptive means that whoever was executing now, if a more urgent task, or better, a task that according to the selection function has higher priority to the executing task, then with a preemptive algorithm, I take the executing task, preempt it, and execute the new task instead. Okay? With a non-preemptive algorithm, instead, the executing task is kept in the processor, it's kept executing until it finishes its execution, and only then will I schedule the next task. Okay? So preemptive or non-preemptive. Just an example. I'm executing, for instance, a low priority task. At this point, a new guy arrives, okay, which has higher priority. For instance, this is tau high, and this is tau low. Okay, I'm using a priority-based scheduler, for instance. So the selection function, is based upon priorities. Okay, so I'm starting executing the low priority one. At some point, the higher priority ones arrives. So if I'm in a non-preemptive algorithm, this guy will continue executing until it finishes, and only then the high priority task will execute. Okay, this happens in a non-preemptive algorithm. Okay, in a preemptive algorithm, instead, this guy is preempted, this guy executes instead. When it finishes, this guy may resume execution and continue. Okay? So what is the difference between a preemptive and non-preemptive? We're going to see that in the schedulability test we're going to develop together. But with a preemptive algorithm, the high priority task will have to wait for less time than with a non-preemptive one. Okay? So with a preemptive algorithm seems to behave much better from a timing perspective with respect to the tasks that are more of interest to us, or for the tasks that have tighter real-time guarantees required. Okay? So with a preemptive algorithm, high priority tasks can execute right away if they are the highest priority tasks there, okay? Or they are the more urgent tasks. While with a non-preemptive algorithm, high priority tasks typically experience some kind of blocking, it's called blocking, okay, due to the non-preemptive execution of lower priority ones, okay? What do I gain with a non-preemptive algorithm? What do you think? What do you gain with a non-preemptive algorithm? So I told you, the drawback of non-preemptive is that you insert blocking times with respect to the high priority one. But is there anything that you may gain with a non-preemptive algorithm?
It's simpler.
It's simpler. This is one.
Context switch.
Context switch. So you have less context switches. Less context switches. You remember, this typically is associated to some overhead. Okay? Less context switches. So this guy can continue executing until the end. Only then this will execute. Instead, with a preemptive context switch, save everything, load the new one, back, reload everything, and continue the whole thing. Okay? So non-preemptive algorithms are simpler to implement, and they do not require, they require less context switches than in the preemptive counterpart. Okay? At the price of introducing some blocking time. So when, in a preemptive algorithm, it is also interesting to understand when a preemption may happen. Here I told you when the task arrives, okay, that's the simpler case, okay? When a new task arrives, it has higher priority, that's a scheduling point, okay? This is a scheduling point. If we are going to see together how a real-time operating system is made, you have either a tick-based approach, so every tick you check the scheduling queue, or what I prefer, the event-based approach. So you check the scheduling function only at certain aperiodic points. So, for instance, when a new process is created, okay, when a new task arrives, okay, that's a scheduling function. Or when a process is unblocked, you remember semaphore, right? So if a task was waiting for some resource, high priority task executing, semlock. No, I cannot because the semaphore is in use by someone else, okay? I suspend myself, okay? If I was scheduled, I'm descheduled, okay? Someone else will execute instead. That someone else, which likely has lower priority, but is holding the shared resource, at some point releases the resource, okay? Okay, so mutex unlock, okay? What does a mutex unlock cause? It checks whether some other processes was waiting that mutex and it unblocks it, so it puts it from the blocked queue to the ready queue again. That's a scheduling decision. So is this unblocked task with a higher priority of the currently executing one? Yes. Then I'm in a preemptive scheduler, take it back and execute it. So preemption arises. So unblocking a semaphore may cause a preemption in a preemptive scheduler. Okay? Releasing a mutex, okay, or a condition variable, so may cause a context switch if you are in a preemptive scheduler. Okay? Interrupts. Again, interrupts, like a new packet is ready in your system from the I/O controller that raises an interrupt to your processor. Is it your process that will deal with interrupts? Is a user process that deals with interrupts? No, of course, it's the operating system. But if you're executing and now you need to execute the OS, that's a context switch, okay? Also, what may this interrupt cause? This interrupt is an interruption of the flow of execution. Why it is not only involved in a context switch, but it may also be involved in a scheduling decision. Because this interrupt, the interrupt service routine that you call, may easily be associated to a task creation. Okay, that's common. So I may have task creation connected to an interrupt. Okay, for instance, someone signals me that a new packet is ready to be treated, or a new frame arrived from a camera, or a new, I don't know, whatever, arrived from a sensor of mine. I have a task, the sensing task, okay, that now is in charge of taking this data, doing something, and sending it to someone else, for instance, okay? So it may be the case that an interrupt causes a new task activation, okay? So these are all points where you may expect a scheduling decision, okay? Or a preemption in a preemptive kernel, okay?
But
Yeah.
how I switch the I have a context switch with a new process is created.
Yeah, for instance, if the process is created through an interrupt, this is something. There are multiple ways in which you can create a process. So the interrupt case I made before is one case. Another kind of interrupt can be a timer. So if you have a strictly periodic process, how can you enforce periodicity in your system? You have timers. So typically what you do is you program a timer, okay? When it fires, this is associated to an interrupt, and this creates a new job for a process, for some kind of activity, okay? The first thing it does is reset the timer and reprogram it again for the rest, execute it, it finishes, okay? Then you execute someone else. When it fires again, okay, this is a new thread creation every period. Another kind of creation, which does not have to do with interrupts or timers, is the task creation by tasks themselves. So a task can be created by other tasks. So task 1, during its execution, can tell, okay, create task 2. Okay, you do that with pthreads. Probably you did that with the exercises in the previous classes, right? So tasks can be created also by other tasks. Okay, so that's also a way new process is created. Okay, and that may involve a scheduling decision. For instance, task 2, which has lower priority than task 1. If task 2 creates task 1, when it creates task 1, there is a preemption because now task 1 is ready. Okay, it executes instead of task 2. Okay. So how to evaluate the quality of a scheduler? Okay. Typically, what we want is responsiveness, responsivity of a system. So you would like your processes to be fast enough. What does fast enough mean? It means according to the timing requirements they have. Okay? If you need to send an email, you don't care that it arrives after a few seconds or after 1 second. Rather, if you are driving a car autonomously, you really need that everything will work in time. Okay? So response time of the processes is something that you evaluate when designing a scheduling algorithm. Okay? I would not use the first in, first out scheduling algorithm for real-time activities because we will show it is not robust enough for the timing requirements you have in a hard real-time systems. Or you may use another kind of criteria, which is throughput. Throughput means how many tasks may I schedule successfully in my system. Throughput also may be a parameter that you're interested in non-real-time application. Typically the scheduler you have here in a general purpose system are based on average latency, on throughput. So you would like to crunch as much data as possible, okay? Because you are not too much interested in the real-time behavior of your general purpose system. You just want data to be crunched sufficiently fast. That's also typical with high-performance computing application, okay? Also typically when you use GPUs, so highly parallel computing architecture, are generally interested in maximizing throughput. So you would just like to eat so much data and processes as you can in a given amount of time, okay? So these are two different criteria. response time and throughput, and they're not always going together. So typically I may privilege response time instead of throughput, or the other way around. Okay? So performance, of course, is important. Okay? Performance is important. You can have a powerful system, but I underutilize it, so I just use 10% of the processing resources. Then that's of course a weakness of your scheduling algorithm. But performance is not the only important thing. Okay? Typically what we do in a real-time system is to sacrifice a little bit of performances to achieve a higher predictability. Okay? Predictability. So predictability is what we showed in the introduction of real-time systems. We are concerned about to deal also with worst-case scenarios. Okay? Another metric may be fairness. Okay? Instead of just maximizing throughput, we may be interested of allowing different processes to make progress in your system and not penalizing one of them. Okay? For instance, in the reader-writer problem, you remember, we don't want to introduce starvation to one of the tasks instead of the other. Okay? So we would like a fair behavior among the tasks that compose your system. CPU bound, IO bound. That's probably a terminology you're familiar with. CPU bound process is a process that utilizes heavily the processor. You know, the processor is not the only interesting engine in your architecture. Processor is one of the interesting engines, of course, but tasks do not only require computational power, okay? Tasks also require accessing memory and I/O, okay? I/O means network or secondary storage or you name it, okay? So a task that does only limited I/O operations, so most of the time it occupies the processor, is typically called CPU bound task. Okay, it heavily utilizes the cores. Okay, for example, a compiler is a heavily CPU bound process, scientific computing programming. There are benchmarking kernels that we use in our lab that heavily utilizes the processor. Only a few times they need to access memory or I/O. The contrary is an I/O bound process, so it's a process that most of the time is waiting for inputs coming from the external. Okay, so many I/O operations, so most of the time I'm waiting an I/O device, I'm waiting an input for the keyboard, I'm waiting for a network packet, I'm waiting for a CAN bus packet, and so on. Most processors, of course, are a mixture of both. Okay? Of course, you can have multiple kinds of processes, CPU bound or I/O bound. In this course, we are mostly concerned with scheduling of CPU, not on scheduling of I/O and memory. Okay? As a research lab, we are also dealing with the scheduling of I/O, memory, and so on. But we are here more focused on the schedule of the CPU, which historically has been the scarce resource to schedule. Okay, so typically you don't schedule something that you have in abundance. You don't schedule the air you have. You schedule what you don't have so often. You have just in a reduced amount. Okay, so the core was the main resource to schedule. Okay, that's why historically the scheduling algorithms were focused on scheduling the processing power. Okay, so definition, feasibility, and schedulability. There is a subtle differences between these two concepts. Okay, you remember here I told you, okay, I give you a set of tasks. Would this task be schedulable or feasible on a given architecture so that their deadlines are met? Or, for instance, in this case, if all of them are together, or this case, if the two of them are together, that would lead in an overload of the system, or in some of the task to miss a deadline. Okay, so let's first read the definition, then I will explain them. So a scheduled sigma is said to be feasible if all the tasks are able to complete within a set of constraints. Okay, so a set of tasks, okay, is feasible. Okay, a schedule is feasible if all the tasks are able to complete within a set of constraints. A task a task set gamma is said to be schedulable if there exists a feasible schedule for it. Okay? So again, a set of tasks, for instance this task, would be schedulable if there exists a feasible schedule for it. Okay?
Are there many feasible schedules for...
That's exactly the case, yes. There may be multiple feasible schedules, okay, for a given set of tasks. Okay? A task may be schedulable with earliest deadline first, or with fixed priority, but not with first in, first out, for instance. Okay? So first in, first out is not a feasible schedule for that task set, while EDF and priority and rate monotonic, for instance, are feasible schedule for that considered task system. Okay? So again we say that a set of tasks is schedulable if there exists a feasible schedule for it. Okay? So the general scheduling problem, given a set of n tasks, okay, maybe aperiodic or maybe recurring or maybe whatever. So gamma is our set of tasks, and a set of m processors, one or more processors, and a set of r shared resources. Okay, because you don't only schedule processor, you also schedule the access to shared resources, shared data structures, for instance. Okay? Then we say that the scheduling problem is the problem of finding an assignment of processor and resources to tasks, okay, which produces a feasible schedule. Again, these are the entities to be scheduled, okay? Our task set, our task system, okay? These are the resources that have to be accessed by this task, mainly one or more cores, one or more processors, okay? Again, I will interchangeably use core and processor, despite they're not the same thing, okay? And a set of resources. So, we say that the scheduling problem is the problem of finding a feasible schedule, so a scheduling algorithm that produces that all tasks will meet their deadlines. Okay? All tasks will meet their deadlines. Okay? So we say we say in that case that schedule sigma is a feasible schedule. Okay? This is the general scheduling problem. So I need to find an algorithm. Okay? A scheduling algorithm that meets all deadlines. Unfortunately, the scheduling problem is not so easy. In the general case, when I have more than one processor, when I have multiple resources to be shared, when I have multiple tasks that may compete for these resources, the problem is NP-hard. NP-hard. How many of you are familiar with the NP-hard notion? Only the computer scientists? Okay, so NP-hard, okay, let me spend some few words about NP-hardness. So this is a very important notion in the algorithmic community, okay? I suggest you to explore. Unfortunately, we will not have time here, but it's one of the topics which are also more philosophically interesting in the computer science. Basically, when I have a problem, okay, I need to find an algorithm to solve it, okay? So try to, I don't know, whatever, sort a queue in an ordered way, okay? I may use multiple algorithms to solve this problem, okay? Of course, I'm interested in the fastest algorithm that solves that problem, okay? So, how fast is the fastest algorithm that I can use for solving that problem, okay? There are multiple measures to define how fast is an algorithm, okay? One of the basic notions is that, for instance, if you are sorting something, it will take more sorting something long than sorting something short. Why am I saying such a basic concept? Because I'm telling you that time it takes to optimally solve a problem depends on your input size, okay? If I have a queue of length 2 or I have a queue of length 2000, of course a 2000 queue will take more time to be sorted, okay? So basically we say that the time it takes for solving a problem is a function of the number of instances of that problem. Again, in the sorting problem, the time it takes to sort this data structure depends on the number of elements that you would like to sort. Okay? In every problem, in every possible problem, you typically have one or more of these parameters. Okay? In the sorting problem, it's just one. It's just the number of elements. If you have the scheduling problem, you may have number of processor, number of tasks, number of resources. Okay? N, M, R. Okay? So this is the input size. Okay? The input size is a set of parameters. It's the magnitude of the input parameters. Okay? Going back to the problem. So in the general computing system, so if I would like to understand how difficult a problem is, I would like to evaluate the function it takes to solve the problem as the magnitude of the input. For instance, so solving a problem may take O of n. I think all of you did analysis, so math, okay? So you are familiar with the big O notion. The big O notion means solving this problem is proportional, okay, to a linear function of n. Okay, so it may take me 3n, okay? So this is O of n. It may take me n plus 1200, okay? This is O of n. So the main complexity is proportional, okay, to a big O notation to n. So this is called linear complexity, okay? But maybe more complex problem may require me n squared. So this is called quadratic complexity. Okay? For instance, I have sorting algorithm that use this kind of complexity. Okay? So one of the simplest algorithms, assume you have a deck of cards, okay? Un mazzo di carte, which is not sorted. What you typically do, you take the second one, and if it is bigger than the first one, you put it later, right? The third one, if it goes in the middle, you put it in the middle. And you go on and on and on and on. I can show you that this algorithm has an O n squared complexity. So in the worst case, it takes a quadratic number of steps based on the input size, which is n. Are you following me? Okay? Are you following me? Interrupt me, because it's the first time you hear that thing. It's probably plausible that you don't understand everything. Okay, n squared typically is still okay, but of course, the bigger n, the worse will be the performance compared to an O of n, okay? I may have even harder problem than that. So this is still polynomial complexity. So every function of n, so if I have an O of n fifth, whenever n is in the base, whenever the input size is in the base of my complexity, this is a polynomial complexity, okay? A polynomial complexity. The problem is when you have the n, which is not in the base, but in the exponent, in the index. Okay? That's a problem, because the bigger n, the more exponentially increases the complexity. Okay? It really gets intractable, that problem. Okay? It gets intractable. So all problems that do not have n in the exponent are called polynomial. Okay? I may even have log n. Log n is a very nice complexity. Is log n better or worse than n? Better, right? Okay, so log n is a very nice complexity. So the best sorting algorithms have a complexity of n log n. Okay? That's a convenient complexity. This is a polynomial. Okay? Bad algorithms or bad problems have an exponential complexity. Okay? They have an exponential complexity. So NP hard does not exactly mean that the complexity is exponential, I don't want to tell you the right definition. You would have to do an algorithm course. It would get too mess in your head now. What we are interested in is that there is a whole class of problem, for which solving them is likely requiring an exponential complexity. Okay? These are NP-hard problems. Okay? It is not sure that they require an exponential complexity, but it's highly likely that their complexity is exponential. Not only that, if I were able to solve just one of these algorithms in polynomial time, so without exponential complexity, then I would be able to solve all of the problems in this class with polynomial complexity. This may seem trivial to you guys, but that would have like enormous repercussion on everything, on the whole computer science. For instance, cryptography, the whole cryptography science, security, is all based on this kind of notion. The whole security, the cryptography, or whatever you have, access prevention protocols that you have everywhere, are based on this notion. So I cannot access a laptop easily because the time it would take for a brute force approach is exponential in the number of characters of my password, for instance. Okay? So if I were able to solve one of these problems, the Chinese remainder problem or whatever you name it, I would be able to crack your laptop in a second. Okay? So that's a very important concept in the computer science. So telling that the scheduling problem is NP-hard tells you, okay, you may be able to solve very simple setting, for instance, one core, few periodic tasks, no resources, in a polynomial time. But when you add cores, or you add resources, or you add fancy task parameters, the problem easily gets to an exponential complexity. Okay? This means NP-hard for the scheduling problem. So it is not at all an easy problem. I'm not showing you optimal algorithms. Okay, I'm showing some optimal algorithms for reduced task sets. Okay? But in general, just if you have two cores, and task set with deadline different than periods, there are no optimal algorithms. There are probably not any optimal dynamic algorithm. Okay? Okay, so here is what I just said. So you may have polynomial time scheduling algorithms which are optimal, but only under restricted conditions. For instance, single cores and periodic tasks. Okay? Just to give you some examples, if you're not familiar with that. So if I have, I don't know, assume you have 30 tasks. Okay, you have 30 tasks. You would like to solve the scheduling problem of 30 tasks. So n is 30. Okay, n is 30. And assume that an elementary step takes 1 second. So your algorithm, your scheduling algorithm, your sorting algorithm, for instance, takes 1 second for each step. Okay? If the number of steps is logarithmic with n, okay, that means that it takes 6 seconds, okay, to solve that problem. If it is linear, it takes 30 seconds, okay, 30, okay, it's an O of 30, okay. If it's polynomial but with index 6, then it takes 12 minutes. But if instead the n is the exponent, okay, in the index, so if it's an exponential complexity, then it takes a little bit more, okay. So this tells you the difference. So here we either have a high index, n to 6 is a high polynomial complexity, but it's not at all comparable to an exponential complexity. Okay? So exponential complexity, you may solve problems of very reduced size, but as the size increases, the problem is intractable. Okay, so let's put ourselves in a more tractable situation. Okay? Let's put ourselves in a setting that we are able to optimally solve. Assume a single core, okay, single core. We have full preemption, okay, so we are not considering the non-preemptive setting for now. So we have full preemptive tasks. We have all tasks simultaneously activated. We will remove this assumption later, but for now we assume all tasks are ready at time 0. Okay, all tasks are there. Okay, no precedence constraints. Okay, tasks shall not wait one for another. Okay, and no resource constraints. Okay, so we don't have mutex locks, unlock, blocking, or whatsoever. Okay. So this is the very simple problem you can have in the scheduling problem, okay? The simplest scheduling problem ever. One processor, set of tasks, everyone ready at time 0, okay? No resources, no precedence constraints, okay? So let's try to see what we can do. A little bit of taxonomy before. So preemptive and non-preemptive we already said, okay? We may use a preemptive scheduler or non-preemptive scheduler, okay? Offline versus online. What does that mean? Offline scheduling means I pre-compute something like a scheduling table where I decide at what time which task will execute beforehand. Okay? So I say from time 0 to 1 will be task 1, from time 2 to 6 will be task 6, from time 6 to 8 will be task 3. Okay, and so on. I know beforehand when each task will execute. Okay. In an online setting, instead, scheduling decisions are taken at runtime, are taken online. I don't have any pre-computed table where I have the scheduling decision. Instead, I decide more online which task to execute next. Okay. So at each moment, I will maybe see which task is ready and decide at that moment which task to execute, okay? So I don't know beforehand which task will be executed. Pros and cons of these two alternatives. Let's guess together. I will tell you. So in the offline scheduler, you need to have a pre-computed table, okay? This occupies memory, okay? If the table is large, this may occupy memory. And the more tasks you have, the more scheduling decision you take, the bigger such a table is. And if you have newly arriving tasks, or you have asynchronous events, or you have events that arrive during your setting that you did not take it into account before, so, okay, the offline scheduling approach is not robust enough to handle that. Okay, so these events were not considered in the pre-computed table offline. Okay, so you are not robust to online events that may arise during your execution. In the online case, instead, typically it's lighter. Okay, so you don't have pre-computed tables, but you don't exactly know when each task will be executed. So you typically for real-time system, you typically have to couple up an online scheduling algorithm with a schedulability algorithm. So in the offline, you know by design when each task will be executed. So you know if deadline will be met or not. You just check the table, okay? You are the one that is enforcing the execution. In the online scheduling algorithm, instead, for instance, you just say, let's execute the task that has the shortest deadline at each moment, at each time, okay? If you don't know their arrival, you don't know what will happen in your system. So you need to recur to some schedulability test to ensure you that everything will work correctly, okay? We are going to see some of these schedulability tests. So static versus dynamic. Static and dynamic means in the scheduler that I enforce, which kind of parameters I take into account of my tasks. So do I only take into account parameters that I know before beginning the execution, or I also take into account parameters that I know once I already began the execution? What do I mean? For instance, task period, priority, execution time, these are typically parameters that you know beforehand, okay? So if you do a scheduler, maybe an online scheduler, that you say it will basically decide to schedule the task which has the shortest period, okay? Or the shortest relative deadline, okay? This is called rate monotony or deadline monotony. So these are static scheduling approach because I knew already beforehand, before starting the execution, these kind of parameters. Okay. Instead, if I base my scheduling decision on something that I know dynamically, that I only know at runtime, for instance, the absolute deadline of a task. So if there is a task that may arrive whenever he wants, okay, the deadline, the absolute deadline, this I didn't know. I knew the relative deadline, okay, I didn't know the absolute deadline, okay? Or if I base my scheduling decision on the arrival time, and I don't know the arrival time, okay, this is for instance first in, first out, okay, I don't know the arrival time, okay? So I base my scheduling decision on the absolute arrival time, so these are all dynamic schedulers, okay? Tell me if I shall repeat. So, best effort versus optimal. Optimal scheduler is a scheduler that if there exists a feasible schedule for that task, then also that scheduler is able to feasibly schedule that task. Or the other way around, if it can never be the case that my optimal scheduler is not able to execute a task set while another scheduler is able to do so. Okay? So an optimal scheduler is basically the best, one of the best scheduler that you can use. So it may never be the case that I'm not able to feasibly schedule a task set while someone else is. So in that case, I'm not an optimal scheduler, okay? And also, if I'm not able to schedule that task, me, optimal scheduler, I'm not able to schedule that task set, then I'm sure that no one else is able to schedule that task set, okay? So whenever someone tells you about optimality, you always have to ask what kind of optimality, okay? Optimal may mean multiple things. In this domain, optimal means what I just told you, okay? Let me repeat it again because it is important. So an optimal scheduler, it's a scheduler that it will never be the case that he is not able to schedule something while someone else is. Or the other way around, if a task set is schedulable according to some scheduling algorithm, then it will be also schedulable with that optimal scheduler. Okay? You can see it in both ways. Okay? This may be convenient for you. So I'm rephrasing it in two ways. So one is A, then B, and the other one is if not B, then not A. Okay? So if a task set is schedulable, then it is also schedulable with our optimal scheduler. Okay? If a task is schedulable, so if there exists a scheduling algorithm to feasibly schedule that task set, okay, then my optimal scheduler is able to schedule it. Here you see, if my optimal scheduler is not able to schedule it, then no scheduling algorithm is able to do so. Okay? So you can see it the other way around. This always holds, okay? When you invert this arrow and you complement, you do the negation of it, then it still holds in the other direction. Okay, so let's re-see here what I just explained you guys. So offline, all scheduling decision taken beforehand, okay? Schedule stored in a table, okay? Online, scheduling decision taken at runtimes may be based on task activation, okay, or on absolute deadlines, okay? Offline versus online. Then what we said, static versus dynamic. So scheduling decisions in a static scheduler are taken based on fixed parameters that I knew beforehand, and dynamic scheduling decisions are based on parameters that can change with time. Okay? Optimal versus the effort. Optimal, I just told you guys, always find a feasible schedule if there exists one. Okay, my schedule is optimal if it always find a feasible schedule when there exists one. Best effort, okay, just try to do my best. Okay, not optimal. Okay, let's try to schedule it. Just the best effort to schedule it. Okay, I try to do my best, but I do not provide any guarantee about it. Okay, optimal tasks, optimal schedulers, sorry, may have a high complexity. Okay, may have a high complexity. Best effort scheduler typically sacrifice complexity for optimality. Okay, so they are not optimal. Okay, but they are so sacrifice optimality for decreasing complexity. Okay, let's see our first after this long taxonomy terminology slides. Let's see finally, eventually, some scheduling algorithms. Okay. These are not so suited, are not so suitable for real-time systems, but they are nevertheless interesting to take a look at. First in, first out is one of the most intuitive ones. Okay, I just schedule the oldest one. Okay, so the one that arrived earlier is the one that, according to some fairness reason, I would like to schedule now. Okay. That's first come, first serve. Shortage of first. Shortage of first means if I know the execution time, the worst case execution time of my tasks, I first execute the smallest task, then the other one, then the other one, so the last one will be the longest one. Okay? This is the shortest job first. Priority scheduling. No need to explain it, right? First the highest priority one, later the lower priority one. Round robin, first one task, another 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay? So it's a round robin scheduling. Okay? Okay, let's see more in detail. First in, first out, or first come, first serve. It assigns the CPU based on the arrival times. Okay? So if you follow me in the terminology, that means decisions are online. I do not know them beforehand. Okay, I just know which one to schedule when they arrive in the system. Okay, and dynamic. So I base my scheduling decision not on something that I knew beforehand, but on something that I know only when it verifies. When the task arrives, then I know which position it will hold in the scheduling queue, in the first in, first out queue, in the ready queue. Okay, can be. So it is non-preemptive because tasks have only one arrival time, so there is nothing that can change that the task arrived at that time. Okay, so there is no possible preemption there. Okay, I don't have any shared resources here, we assume. And it's a best effort, so there is not any guarantee that this kind of scheduler may provide me. Okay, it is not optimal. Okay. So when they arrive, okay, I inserted the last one that arrives at the end, okay, and I always take the first one. Yeah.
Why is dynamic this algorithm?
Yeah, dynamic because the scheduling decisions are based on the arrival time. So the position of a task in this queue, how is it selected? So it is selected based on the arrival time of that task. So if I'm the last one arriving, so I have the latest arrival time, I will be at the end. I will be the last one. If I'm here, it means that I'm the first one among the ready tasks that arrived in the system. Okay? So the position in the ready queue is based not on something that I knew beforehand, but on the arrival time, which is something that is dynamic. Just to make you understand, so a fixed priority scheduler would not sort this queue according to arrival times. It would sort this queue according to priorities. So with a fixed priority scheduler, I would have here maybe the last arrived task, but with highest priority. Okay? So since the priorities, I knew them beforehand, I knew the priority of the task even before they arrived. Okay? This is a static parameter. So that's a static scheduler. Okay? EDF, earliest deadline first, it computes decision based on absolute deadlines. Okay? I know absolute deadline only when the job arrives. Okay? Then I know his deadline. Okay? Again, this is a dynamic scheduler. Okay? Instead, if I base my scheduling decision on relative deadlines, okay, these I know before the task arrives. Okay, I know that the task has a relative deadline of that thing. I don't know exactly when each jobs arrive. I don't know their absolute deadline. I know the relative deadline. So again, this is a static schedule. Okay?
Because I don't know when the task finish.
I don't know exactly. In that case, I don't know. I mean, the scheduling decision is not based on something that you knew beforehand, but you will know for EDF. You will know only when. Exactly. Okay, this is an example of FIFO, first come first serve, FCFS. It's unpredictable. It's unpredictable. What do we mean with unpredictable? Unpredictable is something whose effects may vary significantly based on different settings. So what are we interested at in real-time systems? We are interested in response times. Again, real-time system, not only functional guarantees, but we need to ensure that response time is before the deadline. Okay? That should finish before its deadline. Okay? We are interested in all tasks, all real-time tasks, finishing before their deadlines. Okay? So first come, first served. I base my scheduling decision based on arrival times. Okay? Up arrow is the arrival time. Okay? I have 3 tasks, 3 jobs. They are not recurring tasks, just 3 jobs. Okay? Task 1, task 2, and task 3. Okay? So if task 1 is the first one arrives, it executes, it finishes here. So with a response time of 20. Okay? Task 2 arrives here, so it should execute it after the 1 finishes. So task 2 gets executed here until here. Response time of 26, 28. I don't know. I need to change that. Yes. 26 and 30. Okay. These are, I will change that in the slides. Okay. No, it's correct. Sorry. It's 28 minus the arrival time, which is 2. Okay. So the response time is 26. Okay. Tau 3 arrives here. Okay, so it gets executed after R1, R2, okay, after Tau 1, Tau 2 finished, okay? So Tau 3 will execute it here, and it will finish at time 30, minus its arrival time, which is 4, it leads to a response time of 26, okay? Response time is not the absolute time where it finishes, that's the finishing time. The response time is the finishing time minus the arrival time, okay? That's the response time, big R. Okay, R1, R2, R3, so 20, 26, 26, okay? If things change a little bit, so now it's 3 that arrived before, 2 that arrived second, and 1 that arrived last, this is the schedule that you obtain. So now, the response time of 3 is 2, so significantly smaller than before, okay? From 2 to 26, that's a huge variation, okay? That's not so good for real-time systems. 1 increases from 20 to 26 due to the non-preemption of 3 and 2, okay? And 2 decreases from 26 to 8. So there is a wide variability in the response times of my tasks, okay? It's non-preemptive because, again, scheduling decisions are just based on arrival time. And arrival time may not change. So they cannot change, right? Once they arrive, that's arrival time. So, okay, it's not based on priority. For instance, if you were basing your scheduling decision on priority, at some point a high priority task may arrive here and cause a preemption, okay? But with the FIFO, if a task arrives here, by definition it has lower priority, okay? It cannot cause a preemption, okay? Okay, that was the first one. Let's see the second one. SJF, shorter job first, okay? I always select for execution the task that will execute for less, okay? That has the shortest computation time, okay? The shortest computation time. It may be either preemptive or non-preemptive, okay? I can decide whether to implement it in a preemptive way, so as soon as a shorter task arrives, that makes preemption, or I can just implement it in a non-preemptive way. So let's keep the executing tasks until it finishes, and only then I will enforce preemption. It's static. It is static because decisions are based only on CI. Okay, CI I know beforehand. Okay, that's not the remaining job time. Okay, that's the job time. okay? That the length of the worst case execution time, which is a parameter that I know beforehand. It can be used either online or offline, so I will pre-compute tables based on shorter jobs on worst case execution time and fill in my table, or online, I can decide at runtime which task to execute based on their CI parameter. It minimizes, that's a very interesting property, it minimizes the average response times. It minimizes the average response times, okay? It is not something that is suitable for real-time system. We will not use SJF in real-time system, but still it's a very interesting algorithm to consider, okay? That's the first proof, the first demonstration that we're going to see together, okay? Just to start your brain understanding the kind of proofs that we use in the real-time theory, okay? So again, this is not a real-time scheduling algorithm, but still it has this very nice optimality property. What do you mean with optimality here? That's not an optimality in terms of meeting deadlines, okay? This is not a worst case optimality, that's an average case optimality. So it is the tasks that minimizes average, okay, response times. What do we mean with average response times? You remember before we computed R1, R2, R3, okay? So SJF is the guy that is able to minimize the sum of our i's, so R1, R2, R3, divided the number of tasks. Okay, so I sum R1, R2, R3 divided by 3, okay, and I do different scheduling algorithms. If I use this one, no one can do better than this one. Okay, so the average response times, meaning all my tasks will have a response time. I sum them all, divide by the number of tasks. Okay, that's the average response time of my system. Okay, why it is not what I'm interested at in real-time systems? Because it does not bring with itself the notion of deadline. Okay, I may have tasks which I don't care when they respond. Okay, maybe because the deadline is, I don't know, 1 second away. 1 second is infinite in real-time system. Okay, or I may have very tiny tasks which need to respond between 50 microseconds. Okay, if I give the same importance to the response time of the task I don't care with respect to the task that I do care, so then I'm not utilizing a real-time scheduler, okay? Because it gives the same importance to non-real-time activities and real-time activities, okay? Shorter jobs, instead, give the same importance to all of them, okay? So it minimizes the average response time. Okay, let's see an example here, okay? So, in the real-time theory, proofs are typically made by contradiction. Okay, you know, are you familiar with the proving by contradiction? Okay, so to prove by contradiction, so I need to prove that if A, then B, so then I do, if not B, then not A. Okay, so here what I would like to prove that SJF is optimal. Okay, I need to prove that SJF is optimal. To do that, I prove so that there exists another scheduler, sigma prime, okay, another scheduler, sigma prime, which is different from SJF, okay, which produces an average response time, so sum of our i's divided by n, which is smaller than R, I, N according to SJF. So this is by contradiction. What am I doing here? So I told you, I would like to claim that SJF is optimal. Okay? So it always will lead to the shortest average response time. Okay? In order to prove that, I prove the contrary of it. So I prove that what happens if there exists another scheduler different from shorter job, which has an average response time which is shorter than shorter jobs. Okay? So by contradiction, assume that this holds, okay? By contradiction, assume that this holds, so not B, assume that this holds, then by some manipulations, by some arguments, we will reach a conclusion which contradicts with our premises, okay? This is a proof by contradiction. If I'm reaching that contradiction, it means that the original statement holds, okay? It means that SJF is optimal. Let's take a look at how I did it, okay? Okay, so assume that there exists a different schedule, sigma, for instance, a different schedule that is different from SJF, which has a smaller response time, average response time, okay? Well, this is the schedule, for instance, okay? L is scheduled before S, okay? We assume all jobs ready at the beginning, okay? And at some point, there is a different scheduling decision with respect to the one that SJF would have taken, okay? So this is the first time from the original times where you reach a scheduling decision which is different from that taken by SJF, okay? So at some point, a longer task is executed before the shorter task, okay? This is the first time from the origin of times where you encounter a scheduled decision which is different to the one that SJF would have taken, okay? Then what we do? We manipulate our original assumption. So, okay, what happens if we change them, if we switch them? If we switch those tasks, okay? Let's switch the shortest before and the longer later, okay? The other one before do not change, okay? The other one do not change, okay? We just change those two, okay? We just change those two. Let's now compute what is the average response time, okay? What is the average response time? Okay, we assume that all tasks arrive at time 0, okay? R0 is the same for everyone, okay? So the response time is essentially finishing time minus arrival time. Since we just neglect the arrival time, the response time coincides with the finishing time, okay? So what is the finishing time of these jobs here? For sigma, this is FL, and this is Fs, okay? For sigma prime, what is sigma prime? Is the modification of this scheduler that we assume that different than SJF, but with a shorter response time, okay? By modifying this, by switching these two tasks, okay? This is sigma prime. So the finishing time of S here, okay, is Fs prime, which is probably shorter, is earlier than what it was, the finishing time of L in the previous schedule. Let me repeat. The finishing time in the modified schedule of the S is by definition, is probably shorter than it was the finishing time of L in the previous schedule, okay? Why is that? Because S is shorter than L, okay? Both of them start at the same point, the shorter one finishes first, okay? Nothing difficult, right? So Fs prime is shorter than Fl. What about the other two finishing time? They coincide, okay? They coincide, okay? So these two do not change. So you probably may guess now what we are doing. So if we sum them up, if we go computing these, okay, parameters, so the average response time, we just sum up the finishing time in the first setting and in the other setting, okay? So in this case, Fs prime plus Fl prime. In the other case is Fs and Fl, okay? So since this holds, then also this holds, okay? Because Fl prime and Fs are the same, while this is shorter than this, okay? Then I can generalize that for every other. So this is the average response time as I showed you there, okay? The R is the same for everyone, okay? So in that case, the modified schedule leads to a response time, okay? Average response time, R this is for the average, okay, of the modified schedule has an average response time which is shorter than the original response time of the original schedule. Okay? This is just for a couple of tasks that have been switched. Okay? It does not conclude the proof. Okay? This is just for 2 tasks. I did not recreate the contradiction I wanted. Okay? I did not reach yet here what SJF could have taken as a scheduling decision. Okay? I need to continue. I need to repeat the same switch of shortest, longer, shortest, longer, shortest, longer until the end, until eventually I reach the shortest job decision. So when there will not be any more ordering different, schedule decision different than the one that SJF would have taken, then I'm done. So I continue doing this switch that I show in the first slide, okay, until I reach the schedule that SJF would have taken, okay? And for all these switches, the response time, okay, always goes in a monotonical direction, okay? So the last one is the one with the smallest average response time. Okay? Is it clear? So we proved by contradiction that SJF leads to the shortest average response time. Is it suitable for real-time systems? Well, it is not optimal in the sense of feasibility. It is optimal in the sense of average response times, but as I told you, if we include the deadlines in the task definitions, so if we consider real-time tasks, not just tasks, but real-time tasks. Real-time tasks have associated deadlines. So we have here a case where a scheduler different than SJF meets the deadline. Okay, so tau 1 executes before D1, tau 2 executes before D2, tau 3 executes before D3. What would have SJF taken as a scheduling decision? That would be the scheduling decision for SJF. First the shortest, then the longer, and then the longest. Okay? So the longest one probably misses its deadline. Okay? So it was optimal in terms of average response times. It is not optimal in a real-time sense. I told you, optimality. In which sense? The real-time optimality says that if a task set is scheduled according to some scheduling algorithm, then it is also scheduling according to my optimal algorithm. Okay? In this case, this is not the case, because that task is schedulable according to some algorithm, but is not scheduled according to my algorithm. So my algorithm, SJF, is not optimal from a real-time perspective. Okay? Okay, third scheduler. That's an important one, priority. Very simple one, very, very simple one. Okay? So, thing evolved in time. So, each task is assigned a priority. For instance, I can assign priority from 0 to 255, okay? I have a set of bits that I can assign priority to. Of course, the task with the highest priority is the one that executes next, okay? So, I have task tau 1, tau A with a priority of 100, task tau B with a priority of 2. I first schedule task A because the priority is higher than task B because the priority is smaller, okay? What happens if I have a task with the same priority? Which one do I decide to schedule? I need to specify that, okay? Either I assume that no task may have the same priority, or I need to break ties, si dice in inglese, break ties, quando due task hanno la stessa priorità, c'è come un tie, un tie break, no? Breaking ties vuol dire dirimere queste contese, no? Quando due task hanno la stessa priorità, when two tasks have the same priority, I need to break ties according to some different policies. For instance, I may decide to schedule them in first come, first serve, or round robin. So if two tasks have the same priority, task A and task B, they are both mapped to the highest possible priority, okay, 99. So which one do I execute first? I may decide to queue them in a first come, first served way. So for instance, I schedule before the one that arrived earlier, okay? This is for instance what sched FIFO. Okay, policy does in the Linux. Okay, Linux has a scheduler, of course, you may have guessed that, right? So one of those is priority based. You have priority from 0 to 99, okay, and you basically decide to schedule each task based on priority. But if two tasks have the same priority, you break ties in a first in, first out way. This is just one of the scheduler that is available in Linux, okay? Another one is sched deadline, which is implementing something similar to EDF, earliest deadline first. Actually, our group, when I was in Sant'Anna, was developed that scheduler. So, can a priority scheduler be used for real-time purposes? If a priorities are assigned in a proper way, yes. So if I decide priorities, taking into account the timing parameters of my task system, then a fixed priority scheduler may be suitable for real-time activities. Okay? So it's one of the convenient schedulers that we use in real-time systems. Okay? It may be static or dynamic, depending on these priorities changing over time or not. Okay? So priority scheduling, it may be fixed priority or dynamic priority. Okay? Fixed priority again is if I give a priority from 0 to 99. Dynamic priority if I give priorities based on deadlines of a given job, absolute deadlines of a given job, or arrival time of a given job. Okay? And again, maybe preemptive or non-preemptive. It's not in the slide, but again, it can be preemptive scheduler or a non-preemptive scheduler. It may happen that a priority scheduler adds starvation to low priority tasks. If I keep executing high priority tasks, the low priority one may starve, okay? But maybe I don't care, okay? It's often the case that I don't care. For countering this problem, the starvation problem, I may enforce scheduling algorithm. I don't use that much, but it's an option. If I want to allow a low priority task not to start too much, I may increase his priority if I'm not executing it for a long while, okay? In previous schedulers that have been implemented in Linux and other systems, there was this kind of aging solving problem that increases the priorities of low priority tasks for avoiding them to starve. Okay? So note that the scheduler we saw before are an instance of priority scheduling. It just varies the way we define priorities. Okay? If we define priorities based on execution time, rather on the reciprocal of the execution time, that's essentially shortage of first. Okay? Shortage of first just tells you, okay, I assign priorities, fixed priorities, static priorities, based on the inverse of the worst case execution time. Okay? That's a priority scheduler, just it happens to be the SJF. If I instead assign priorities based on the arrival times, okay, that's a FCFS. Okay? So both algorithms we saw before are an instance of a priority-based scheduler. Okay? It just varies the way I define priorities. The last, round robin. Round robin is similar to a first in, first out, only I implement the notion of time quantum. Okay, so I have a time interval for which I allow my tasks, my job to execute before enforcing a preemption. Okay? So first come first serve is a non-preemptive one. I just execute the one with the earliest arrival until it ends, and then the second one, and so on. In a round robin, I typically allow a given task to execute for a while. After after a timer fires, for instance, I preempt it and I execute another one. So you re-put the one that is expired at the back of the queue. I execute a new one. If it finishes, okay, I take the last one. If the last one did not finish before the timer expires, I will re-queue it again at the end. Okay? So it's a first in, first out with this time quanta defined for each task. Okay? So no task can execute more than a given time quantum assigned either globally to the system. I, for instance, have a tick, a scheduling tick, or assigned for that particular task. Okay, I can have different time quanta for each of the tasks. Okay, that's a typical way for implementing a round robin schedule. Okay, here is an example. So if n is the number of tasks in the system, and I have a time quantum which is the same for all tasks, okay, I have n tasks. So this is my interval, my scheduling interval, 1, 2, 3, right, n is 3, okay? And that's repeated over and over until one of the tasks finishes. If I asked you, what is the response time of a task here, okay? What is the response time of a task here? Well, it is proportional to this interval here, okay? It is proportional to this interval here, okay? Depending on how many slots my blue task will need, okay? If my blue task may finish in one slot, then it will just that slot. But if my task requires 2 slots, it will be nq plus another slot. If it requires 3 slots, it's twice nq plus that slot. So you have multiple slots based on the ratio of ci over qi. Okay, it's not exactly equal. Okay, it's proportional to this thing. Okay, it would be easy to compute the exact amount. Just to tell you that here we are interested in saying that the response time heavily depends on these macro periods that you do in your round robin scheduling. Okay, so basically it's proportional, okay, to the computing time, to your computing time, okay, and the number of tasks. So the more tasks you have, the larger will be your response time, okay? So response time heavily depends on the number of tasks co-scheduled with you in your round robin schedule, okay? This is an approach that is used often in virtual machines on time-triggered systems. So pretending to have a dedicated processor when you have just 1/10 of that processor, when you just have a share of that processor, which is time shared in a round-robin way. Okay? So it is like the task is executing alone in a virtual processor which is just slower, is n times slower than the original one. Okay? Round-robin schedule. Okay, so what happens if your time quantum is greater than the maximum execution time among the tasks scheduled with the round-robin schedule? Essentially, no task will ever be interrupted by the quantum expiration. Okay? And in that case, round-robin coincides with first come, first served. Okay? If the quantum is sufficiently large, I will never preempt a task during this execution, but will be just a non-preemptive first in, first out schedule. Okay? So the quantum size impacts the context switch, the number of context switches that you have, and the response time. Okay? If the quantum is sufficiently large, then I return back to a first come, first served schedule. Okay? So if the quantum is proportional to the context switch time, then we may factor in the context switch time. Okay? So if there is a context switch here, it is better to put it and considering it, okay? If I need in a real-time system to derive the response time, it is good to consider not only the interference of other tasks, but also the time it takes for a context switch, okay? So now my macro interval will be not only n times q, but n times q plus the context switch time, okay? This increases the response time, which using the same formula we saw before, just adding the delta, the context switch time, reduces to something like this, okay? Reduces to something like this. Now I cannot simplify the q, because I have an additional context switch time there, but it's a formula worth exploring, okay? Again, my response time is a function of n and c, okay? But it's also a function of the context switch time. The context switch time gets more important as q decreases. Again, the context switch time becomes dominant, will have a much stronger impact the shorter is the quantum that you adopt. So if the quantum is short, this factor here will increase significantly, okay? But that's intuitive, right? If I use very short quantum, then I will be always busy context switching rather than doing actual computation, okay? That's an intuitive effect, okay? So, just to tell you that the round robin, for evaluating the response time, there is an overhead impact which increases significantly when, whose impact increases significantly when the quantum size is reduced, okay? Okay, I think that's a convenient preemption point also for us, and I will see you guys next Monday, okay? Have a nice weekend.